two-dimensional nanoporous materials such as graphenes and graphene oxides have attracted a lot of interest in recent years for the separation of a wide variety of mixtures of light gases such as hydrogen carbon dioxide, hydrogen nitrogen, hydrogen methane, carbon dioxide nitrogen, and carbon dioxide methane. Graphenes are also suggested for separations of water alcohol mixtures and in water purification. The topic I'm going to address today is on transport of gaseous components across nanoporous graphene membranes. The material I'm presenting is essentially that I presented in my paper on the Maxwell-Stefan description of mixture permeation across nanoporous graphene membranes, published in 2018 in Chemical Engineering Research and Design. There are basically two pathways for transmembrane transport of gaseous gas molecules. That is shown in the schematic. One is the fluid phase pathway that is shown by the green arrow. This pencil-like molecule is CO2. The green circles are methane. So CO2 and methane can be transported along the fluid phase pathway through the pores. Another mechanism for transport involves absorption of the guest components CO2 and methane onto the graphene surface, surface diffusion, and pore translocation. The contributions of these various pathways can be quantified, and I restrict today my discussions to the Maxwell-Stefan description of surface diffusion of gaseous adsorbed species along the surface of the graphene. Let us consider the motion of two gas species, green and red, components 1 and 2. These could be, say, methane and carbon dioxide as they traverse along the surface of the graphene membrane. For modeling purposes, we consider the gaseous components to hop from one vacant site on the graphene surface to the adjacent one. These vacant sites are adsorption sites on the graphene surfaces, indicated by these oval-shaped white areas. The diffusivity of the two components are described by a simple lattice model as being proportional to the jump frequency nu times the square of the jump distance lambda. This quantity here, zeta, is the coordination number. For a two-dimensional square lattice, the coordination number zeta equals 4. we note that each of the components can move from one adsorption site to the other. Now, let us say that 2 is component CO2 and is most strongly adsorbed onto the graphene surface. There is a further mechanism that needs to be taken into account, and that is that component 1 occupies an adsorption site that has just recently been vacated by the most strongly adsorbed component 2. So there is a possibility that if the occupancies of the adsorbed species on the graphene surface increases, the faster moving component, say methane, has to wait its turn for the adsorption sites to be vacated by the partner CO2 molecules before it can occupy that position on the graphene surface. So schematically, if the green species methane is the more mobile species, then its trajectory of motion along the graphene surface is restricted to this area because the tardier partner CO2 has to vacate its site before that site can be occupied by the more mobile methane that is colored in green. Now, in setting up the flux relationships, it is most convenient to adopt the Maxwell-Stefan formulation that basically is a balance between the force acting on a species that causes a relative motion and the friction that species experiences in its motion along the surface. There are 2 types of frictional contributions for component 1. One is the contribution with to the friction with respect to the solid surface, and in this case we represent the that solid surface as being represented by vacant sites. So the frictional contribution is proportional to the relative motion of species 1 with respect to the vacant sites. That frictional contribution is proportional to the fractional occupancy of the vacant sites. So it is proportional to theta V. The constant of proportionality is a drag coefficient. R is the gas constant, T is the temperature. And this is the Maxwell-Stefan diffusivity for describing the mobility of species 1 with respect to the vacant sites. So D sub 1V. The frictional term is RT divided by D1V times the fraction of the number of vacant sites times the relative motion between component 1 and the vacancy. In addition, there is another frictional contribution that describes the friction between 1 and 2. This is essentially a description of how the motion of species 1 correlates with that of species 2. If species 1 is the more mobile molecule, its motion or its mobility is retarded because of the slow vacation of adsorption sites by the tardier partner, species 2. So this contribution to the frictional term is also called the slowing down term due to correlation effects. The force acting on each of these species is the gradient of the chemical potential, and that can be written in terms of the gradients in the partial pressures in the bulk gas phase. The formulation for component 2 follows exactly the same lines as for component 1. The force acting on component 1 is the gradient of the chemical potential of component 1 is balanced by friction. Component 2 experiences in undergoing relative motion with respect to species 1, and the friction it experiences on undergoing relative motion with respect to the vacancies. There are basically 3 Maxwell-Stefan diffusivities describing surface diffusion. D1, D2 with respect to the solid surface, and D12, which is the description of the correlation between the motion of species 1 with respect to species 2. D12 equals D21, which is due to the Onsager reciprocal relationship.